Hello everyone. In this lecture we are going to study the manual transmissions and the transaxles. The transmission or transaxles is a vital link in the powertrain of any modern vehicle. The purpose of the transmission or transaxle is to use gears of various sizes to give the engine a mechanical advantage over the driving wheels. During normal operating conditions, power from the engine is transferred through the engaged clutch to the input shaft of the transmission or transaxle. Gears in the transmission or transaxle housing alter the torque and speed of this power input before passing it on the other component in the drivetrain. Without the mechanical advantage the gearing provides, an engine can generate only limited torque at low speeds. Without sufficient torque, moving vehicle from standing start would be impossible. In any engine, the crankshaft always rotates in the same direction. If the engine transmitted its power directly to the drive axle, the wheels could be driven only in one direction. Instead, the transmission or transaxle provides the gearing needed to reverse direction so the vehicle can be driven backward. There is also a neutral position that stops power from reaching the drive wheels. So what's the difference between the transmission and the transaxle? Vehicles are propelled in one of three ways: by the rear wheels, by the front wheels, or by the front and rear wheels. The type of a drive system used determines whether a conventional transmission or transaxle is used. Vehicles propelled by the rear wheels normally use a transmission. Transmission gearing is located within an aluminum or iron casting called the transmission case assembly. The transmission case assembly is attached to the rear of the engine, which is normally located in the front of the vehicle, and the drive shaft links the output shaft of the transmission with a differential and the drive axle located in a separate housing at the rear of the vehicle. The differential splits the drive line power and redirects it to the two rear drive axles, which then pass it on to the wheels. Also, we have the front wheel drive or FWD. Front wheel drive vehicles are propelled by the front wheels. For this reason, they must use a drive design different from the rear wheel drive vehicle. The transaxle is the special power transfer unit commonly used in a four-wheel drive vehicles. A transaxle combines the transmission gearing, differential, and the drive axle connections into a single case housing located in the front of the vehicle. So this design offers many advantages. One major advantage is the good traction on slippery roads due to the weight of the drivetrain component being directly over the driving axles of the vehicle. It's also more compact and lighter than the transmission of a rear-wheel drive vehicle. Transverse engine and transaxle configurations also allow for lower hood lines, thereby improving the vehicle's aerodynamics. Also, we have the four-wheel drive vehicles typically use a transmission and transfer case. The transfer case mounts on the sides or back of the transmission. A chain gear drive inside the transfer case receives power from the transmission and transfers it to two separate drive shafts. One drive shaft connects to a differential on the front drive axle. The other drive shaft connects to a differential on the rear drive axle. Most manual transmissions and transaxles are constant mesh, fully synchronized units. Constant mesh means that whether or not the gear is locked to the output shaft, it's in a mesh with its counter gear. All gears rotate in the transmission except for reverse gear. As long as the clutching is engaged, fully synchronized means that the unit uses mechanisms of rings and the clutches to bring rotating shafts and gears to the same speed before shifts occurs, and this promotes smooth shifting. And let's study right now the transmission designs. All automotive transmissions or transaxles are equipped with a varied number of forward speed gears, a neutral gear, and one reverse speed. Transmissions can be divided into grouping based on the number of forward speed gears they have. 5-speed transmissions and transaxles are now the commonly used units, and some of the early 5-speed units were actually 4 speeds with an added on fifth or overdrive gear. Overdrive gear reduces engine speed at a given vehicle speed, which increases top speed and improves fuel economy and lowers engine noise. Most late model 5-speed units incorporate fifth gear in their chain assemblies. This is also true for the 6-speed transmissions and the transaxles. The fifth and sixth gears are included in the main assembly and typically provide 2 overdrive gears. The addition of the 2 overdrive gears allow the manufacturers to use lower final drive gears for acceleration. The fifth and sixth gear reduces the overall gear ratio and allow for slower engine speed during highway operation. And let's move right now to study in depth the gears. The purpose of the gears in a manual transmission or transaxle is to transmit rotating motion. Gears are normally mounted on a shaft and they transmit rotating motion from one parallel shaft to another. Gears and shafts can interact in one of 3 ways. The shaft can drive the gear can drive the shaft, or the gear can be free to run on the shaft. In this last case, the gear acts as an idler gear. Sets of gears can be used to multiply torque and decrease speed, increase speed, and decrease torque, or transfer torque and leave speed unchanged. Let's move right now to discuss gear design. Gear pitch is a very important factor in a gear design and operation. Gear pitch refers to the number of teeth per given unit of pitch diameter. A simple way of determining gear pitch is to divide the number of teeth by the pitch diameter of the gear. We have the spur gears. The spur gear is the simplest gear design used in a manual transmission and transaxles. Spur gear teeth are cut straight across the edge parallel to the gear shaft. During operation, meshed spur gears have only one tooth in a full contact at a time. Its straight tooth design is the spur gear's main advantage. It minimizes the chances of popping out of gear, an important consideration during acceleration and deceleration and reverse operation. For this reason, spur gear are often used for the reverse gear. Also, there is another type of gears, which is the helical gears. A helical gear has teeth that are cut at an angle or are spiral to the gear's axis of rotation. This configuration allows 2 or more teeth to mesh at the same time, which distribute tooth load and produces a very strong gear. Helical gears also run more quietly than spur gears because they create a wiping action as they engage and disengage the teeth on another gear. One advantage is that helical teeth on a gear cause the gear to move forward or aft on a shaft. Depending on the direction of the angle of the gear teeth, the axial thrust must be absorbed by thrust washer and other transmission gears, shafts, or the transmission case. Also, we have the idler gears. An idler gear is a gear that is placed between a drive gear and a driven gear. Its purpose is to transfer motion from the drive gear to the driven gear without changing the direction of rotation. Idler gears are used in reverse gear trains to change the directional rotation of the output shaft. And let's discuss right now the transmission or transaxle design. The internal components of a transmission or a transaxle consist of a parallel set of metal shafts on which mission gear sets of different ratios are mounted. By moving the shift lever, gear ratios can be selected to generate different amount of output torque and speed. The gears are mounted or fixed to the shafts in a number of ways. They can be internally splinted or keyed to a shaft. Gears can also be manufactured as an integral part of the shaft. Gears that must be able to freewheel around the shaft during certain speed ranges are mounted to the shaft using bushings and bearings. The shaft and gears are contained in a transmission or transaxle case or housing, and the components of the housing include the main case body, side or top cover plates, extension housing, and bearing retainers. The middle components are bolted together with a gasket providing a leak-proof seal at all joints. The case is filled with a transmission fluid to provide constant lubrication and cooling for the spinning gears and shafts. And we'll move right now to the transmission features. Most transmissions have three basic shafts: the main shaft, input shaft, and counter shaft. The speed gears ride on the main shaft. The main shaft is also called the output shaft. The input shaft is in line with the main shaft but is not directly connected to it. This shaft and its clutch gear rotates with the clutch assembly and drives the counter gear assembly. The counter gears in turn cause the speed gears to rotate. The counter shaft assembly is often referred to as the cluster gear. The counter shaft is actually several gears machined out of a single piece of steel or iron. The counter shaft may also be called the counter gear or cluster gear. The counter gear mounts on a roller bearings on the counter shaft, and the counter shaft is pinned in a place and doesn't turn. Thrust washers control the amount of end play of the unit in the transmission case. The main gears on the main shaft or output shaft transfer rotation from the counter gears to the output shaft. The main gears are also called the speed gears. They are mounted on the output shaft using roller bearings, and the speed gears freewheel around the output shaft until they are locked to it by the engagement of their shift synchronizer unit. Power flows from the transmission input shaft to the clutch gear. The clutch gear meshes with the large counter gear of the counter gear clusters, and this cluster gear is now rotating since the cluster gear is meshed with the speed gear on the main shaft. The speed gears are also turning. There can be no power output until one of the speed gears is locked to the main shaft, and this is done by activating a shift fork, which moves its synchronizer to engage the selected speed gear to the main shaft. Power travels along the counter gear until it reaches this selected speed gear. It then passes through this gear back to the main shaft and out of the transmission to the drive line. And let's discuss right now the transaxle features. Transaxles use many of the designs and operating principles found in a transmission, but because the transaxle also contains the differential gearing and drive axle connections, there are major differences in some areas of operation. Transaxle typically has two separate shafts, an input shaft and an output shaft. The input shaft is the driving shaft. It's normally located above and parallel to the output shaft. Because the input shaft in most transversely mounted transaxle are supported by bearings in the housing, these units do not need a pilot bearing or bushing to support the portion of the input shaft that extends into the clutch assembly. This type of shaft is called a self-centering shaft. The output shaft is the driven shaft. The transaxles main gear freewheel around the output shaft unless they are locked to the shaft by their synchronizer assembly. The main speed gears are in constant mesh with the input shaft drive gears, and the drive gears turn whenever the input shaft turns. A pinion gear is machined into the end of the transaxle pinion shaft. This pinion gear is in constant mesh with the differential ring gear located in the lower portion of the transaxle housing. Because the pinion gear is part of the pinion shaft, it must rotate whenever the pinion shaft turns. With the pinion rotating, engine torque flows through the ring gear and differential gearing to the drive shafts and driving wheels. And let's move to another important part, which is the synchronizers. The synchronizer performs a number of jobs vital to transmission transaxle operation. Its main job is to bring components that are rotating at a different speed to a one synchronized speed. A synchronizer ensures that the pinion shaft and the speed gear are rotating at the same speed. The speed major job of the synchronizer is to actually lock these components together. The end result of these two functions is a clutch-free shift. In some transmissions, a synchronizer can have another important job. When spur teeth are cut into the outer sleeve of the synchronizer, the sleeve can act as a reverse gear and assist in producing the correct direction of rotation for reverse operation. In modern transmissions and transaxles, all forward gears are synchronized. One synchronizer is placed between the first and second gears on the pinion shaft, another placed between the third and fourth gears on the main shaft. If the transmission has a fifth gear, it's also equipped with a synchronizer. A reverse gear is not normally fitted with a synchronizer. A synchronizer requires gear rotation to do its job, and reverse is selected with the vehicle at the stop. And let's discuss right now the synchronizer design. The most commonly used synchronizer, a block or cone synchronizer. The synchronizer sleeve surrounds the synchronizer assembly and meshes with the external splines of the clutch hub. The clutch hub is splined to the transmission pinion shaft and is held in a position by a snap ring. A few transmissions also use pin-type synchronizers. The synchronizer sleeve has a small internal groove and large external groove in which the shift forks resets. 3 slots are equally spaced around the outside of the clutch hub. Inserts fit into these slots and are able to slide freely back and forth. These inserts, sometimes referred to as shifter plates or keys, are designed with a ridge in their outer surface. Insert springs hold the ridge in a contact with a synchronizer sleeve internal groove. The synchronizer sleeve is precisely machined to slide into the clutch hub smoothly. The sleeve and hub sometimes have alignment marks to ensure proper indexing of their splines where assembling to maintain smooth operation. Brass, bronze, or powdered iron synchronizing blocking rings are positioned at the front and rear of each synchronizer assembly. Some synchronizer assemblies use additional frictional material on the blocking rings to reduce slippage. Each blocking ring has 3 notches equally spaced to correspond with the 3 insert keys of the hub. Around the outside of each blocking ring is a set of beveled clutching teeth. The inside of the blocking ring is a shape like a cone. This cone surface is lined with many sharp grooves. The cone of the blocking ring makes up only one half of the total cone clutch. The second or matching half of the cone clutch is part of the speed gear to be synchronized. And let's study right now the operation. When the transmission is in a neutral or reverse, the first, second, and third, fourth synchronizers are in their neutral position and are not rotating with the pinion shaft. Gears on the main shaft are meshed with their counter shaft partners and are freewheeling around the pinion shaft at various speeds. To shift the transmission into first gear, the clutch is disengaged and the gear shift lever is placed in the first gear position. This forces the shift fork on the synchronizer sleeves toward the first speed gear on the pinion shaft. As the sleeve moves, the insert also moves because the insert ridges lock the insert to the internal groove of the sleeve. The movement of the insert forces the blocking ring's cone friction surface against the cone surface of the first speed gear shoulder. When the blocking ring and gear shoulder come into contact, the grooves on the blocking ring cone cut through the lubricant film on the first speed gear shoulder and a middle-to-middle contact is made. The contact generates substantial friction and heat. This is one reason bronze or brass blocking rings are used. A non-ferrous metal such as a bronze alloys minimize wear on the hardened steel gear shoulder. This frictional coupling is not strong enough to transmit loads for long periods. As the components reach the same speed, the synchronizer sleeves can now slide over the external clutching teeth on the blocking ring and then over the clutching teeth on the first speed gear shoulder. This completes the engagement. Power flow is now from the first speed gear to synchronizer sleeve to the synchronizer clutch hub to the main output shaft and out to the drive line. And to disengage the first speed gear from the pinion shaft and shift into second speed gear, the clutch must be disengaged as the shift fork is moved to pull the synchronizer sleeve and disengage it from the first gear. As the transmission is shifted into second gear, the inserts again lock into the internal groove of the sleeve. As the sleeve moves forward, the forward plugging ring is forced by the insert against the cone friction surface on the second speed gear shoulder. Once again, the grooves on the blocking ring cut through the lubricant on the gear shoulder to generate frictional coupling that synchronizes the speed gear and shaft speeds. The shift fork can then continue to move the sleeves forward until it slides over the blocking ring and the speed gear shoulder clutching teeth, locking them together. Power flows now from the second speed gear to the synchronizer sleeve to the clutch hub and out through the pinion shaft. And let's discuss right now the gear shift mechanisms. A typical transmission shift linkage for a 5-speed transmission. As you can see, there are 3 separate shift rails and forks. Each shift rail, shift forks, is used to control the movement of synchronizer, and each synchronizer is capable of engaging and locking 2 speed gears to the main shaft. The shift rails transfer motion from the driver-controlled gear shift lever to the shift forks. The shift forks are semicircular casting connected to the shift rails with split pins. The shift fork rests in the groove in the synchronizer sleeves and surrounds about one half of the sleeve circumference. The gear shift lever is connected to the shift forks by means of the gear shift linkage. Linkage designs vary between manufacturers but can generally be classified as being direct or remote. Also, we have the gear shift linkages. There are two basic designs of gear shift linkages: internal and external. Internal linkages are located at the side or top of the transmission, and the control end of the shifter is mounted inside the transmission, as are all of the shift controls. Movement of the shifter moves a shift rail and a shift fork toward the desired gear. This moves the synchronizer sleeve to lock the selected speed gear to the shaft. This type of linkage is often called a direct linkage because the shifter is in direct contact with the internal gear shifting mechanisms. Shift rails machined with interlock and detent notches. The interlock notches prevent the selection of more than one gear during shifting. When a shift rail is moved by the shifter, interlock pins hold the other shift rails in their neutral position. The detent notches and matching spring-loaded pins or balls gives the driver feedback as to when the shift collar is adequately moved. As the shift rail moves, a detent ball moves out of its detent notch and drops into the notch for the selected gear. At the same time, an interlock pin moves out its interlock notch and into the other shift rails. External linkages function in much the same way, except that rods external to the transmission are connected to levers that move the internal shift rails of the transmission. Some transaxles are shifted by rods or by cable. And right now we are gonna go through the transmission power flow. So let's discuss the path of power through a typical 5-speed transmission. And let's start with the neutral. When the gear selector is placed in the neutral position, the input shafts rotate at engine speed. The shaft's clutch gear is in a mesh with the counter gear, which rotates on the counter shaft. The counter gears are in mesh with the speed gears because none of the speed gears are locked to the main shaft. The gears spin freely and no torque is applied to the main shaft. All gear changes pass through the neutral gear position. When changing gears, one speed gear is disengaged, resulting in a neutral before the choosing gear is engaged. And we'll move to the first gear. First gear, power or torque flows through the input shaft and the clutch gear to the counter gear. So the counter gear rotates and the first gear on the cluster drives the first speed gear on the main shaft. When the driver selects first gear, the second synchronizer moves to the rear to engage the first speed gear and lock it to the main shaft. The first speed gear drives the main shaft, which transfers power to the drive line. Also, we have the second gear. When the shift from first to second gear is made, the shift fork disengages the second synchronizer from the first speed gear and moves it until it locks the second speed gear to the main shaft. Power flow is still through the input shaft and the clutch gear to the counter gear. However, now the second counter gear on the cluster transfers power to the second speed gear locked on the main shaft. Power flows from the second speed gear through the synchronizer to main shaft and drive line. In second gear, the need for vehicle speed and acceleration is greater than the need of maximum torque multiplication. To meet these needs, the second speed gear on the main shaft is designed slightly smaller than the first speed gear. And Let's move to the third gear. When the shift from second to third gear is made, the shift fork returns the first second synchronizer to its neutral position. A second shift fork slides the third fourth synchronizer until it locks the third speed gear to the main shaft. Power flow now goes through the third gear of the counter gear to the third speed gear, through the synchronizer to the main shaft and the drive line. Third gear permits a further decrease in torque and increase in speed, and as you can see, the third speed gear is smaller than the second speed gear. And let's discuss right now the fourth gear. In fourth gear, the third fourth synchronizer is moved to lock the clutch gear on the input shaft to the main shaft. This means power flows directly from the input shaft to the main shaft at a gear ratio of 1:1. This ratio results in maximum speed output and no torque multiplication. So fourth gear has no torque multiplication because it's used at cruising speeds to promote maximum fuel economy. The vehicle is normally downshifted to lower gears to take advantage of torque multiplication and acceleration when passing slower vehicles or climbing grades. And we have the fifth gear. When fifth gear is selected, the fifth gear synchronizer engages fifth gear to the main shaft. This causes a large gear on the counter shaft to drive a smaller gear on the main shaft, which result in an overdrive condition. Overdrive permits an engine speed reduction at higher vehicle speeds. And the last one is the reverse. In reverse gear, it's necessary to reverse the direction of the main shaft or the output shaft. This is done by introducing a reverse idler gear into the power flow path. The idler gear is located between the counter shaft reverse gear and the reverse speed gear on the main shaft. The idler assembly is made of a short drive shaft independently mounted in the transmission case parallel to the counter shaft. The idler gear may be mounted near the midpoint of the shaft. The reverse speed gear is actually the external tooth sleeves of the first-second synchronizer. When reverse gear is selected, both synchronizers are disengaged and in the neutral position in the transmission. The shifting linkage moves the reverse idler gear into mesh with the first-second synchronizer sleeve. Power flows through the input shaft and the clutch gear to the counter shaft. From the counter shaft, it passes to the reverse idler gear, where it changes rotational direction. It then passes to the first-second synchronizer sleeve. Rotational direction is again reversed. From the sleeve, power passes to the main shaft and the drive line. And let's study right now the transaxle power flows. The transaxle that we are gonna study is a 5-speed with 2 shaft units. Let's start with the neutral. When a transaxle is in its neutral position, no power is applied to the differential. Because the synchronizer colors are centered between their gear positions, the meshed drive gears are not locked to the output shaft. Therefore, the gears spin freely on the shaft and the output shaft doesn't rotate. We have the forward gears. When first gear is selected, the first-second gear synchronizer engages with the first gear. Because the synchronizer hub is split to the output shaft, first gear on the input shaft drives its mating gear, first gear, on the output shaft. This causes the output shaft to rotate at the ratio of first gear and to drive the differential ring gear at the same ratio. As the other forward gears are selected, the appropriate shift fork moves to engage the selected synchronizer with the gear. Because the synchronizer's hub is split to the output shaft, the desired gear on the input shaft drives its mating gear on the output shaft. This causes the output shaft to rotate at the ratio of the selected gear and drive the differential ring gear at the same ratio. And let's move to the reverse. When reverse gear is selected on a transaxle that use a sliding reverse gear, the shifting fork forces the gear into mesh with the input and output shafts. The addition of this third gear reverses the normal rotation of first gear and allows the car to change direction. And let's discuss right now the differential action. The final drive ring gear is driven by the transaxle's output shaft. The ring gear then transfers the power to the differential case. The case holds the ring gear with its mating pinion gear, and the differential side gears are connected to the drive axle. One major difference between the differential in a rear-wheel drive car and the differential in the transaxle is direction of power flow. In rear-wheel drive differential, the power flow changes 90 degrees between the driven pinion gear and the ring gear. This change in direction is not needed with most four-wheel drive cars. The transverse engine position places the crankshaft so that already is rotating in the correct direction. Therefore, the purpose of the differential is only to provide torque multiplication and divide the torque between the drive axle shafts so that they can rotate at different speeds. Let's move to the final drive gears and overall ratios. All vehicles use a differential to provide an additional gear reduction and torque increase. So above and beyond what the transmission or transaxle gearing can produce, this is known as the final drive gear. In a transmission-equipped vehicle, the differential gearing is located in the rear axle housing. In a transaxle, however, the final reduction is produced by the final drive gears housed in the transaxle case.